Okay. Hi everyone. So welcome back. So this is lecture 6 and today we'll be looking at support vector machines with Slack. Right. So in lecture 4 and lecture 5 we have looked at the linear separability case. Right. So we assumed that the data is linearly separable and then we formulated the support vector machines. And in lecture 5 we looked at the dual formulation again in the linearly separable case. Right. So now we will actually go to the non-linearly separable case and we'll do this through the introduction of the Slack variables. Okay. So I'll just recap the formulation of SVM in the linearly separable case, right? So if you recall, we had minimum of the norm of W square, right? So I want to maximize the margin such that Yi multiplied by W transpose Xi plus V. So this is the model, right? This should be greater than or equal to 1, right? Or equivalently, you can write this as you can write this as basically I take this on this side and 0 greater than 1 minus that, right? Or equivalently 1 minus Yi of W transpose Xi plus V is less than or equal to 0, right? So this is the kind of SVM formulation, right? And then in the last class we saw how we can compute the Lagrangian of this, right? And we can compute the Lagrangian by looking at by actually writing the Lagrangian as L of W comma B comma lambda, right? So I'm including Lagrange multipliers lambda over here, and basically I will have this as norm of W square plus, right? So I'm going to use this expression because in the Lagrange multipliers I have basically Fi of x less than or equal to 0, right? And then I have this plus the sum of I from 1 to capital M of lambda I, right, multiplied by 1 minus Yi of W transpose Xi plus E, right? And essentially in my Lagrangian, what I need to do is that I can construct the dual now, right? So my dual is basically G lambda, right, as a function of lambda is essentially where I can take a max, or sorry, I take a min over my W, right? And I'm trying to maximize this over lambda. So I take a min over W comma B of this term, right? And if you recall from the last lecture, we can actually compute this easily, right? So the way we can compute this is by taking the derivative with respect to W, and then we will get a term of W equal to something, right? And then we can plug in the value of W that we get, right? And essentially once we plug in the value of W, we get this equation in terms of lambda, right? And this equation is nothing but this term, which is minus half of the sum of I sum of j lambda I lambda j multiplied by yi yj, right? And this kernel term, which is xi transpose xj, right? So it's basically a product between every so this sum is from I from 1 to capital N, and this is from j from 1 to capital N, right? So this is basically a M cross M matrix. So we saw this last time, and then my lambda is basically in R raised to N. So I think one thing, sorry, we do actually have a half over here in the typical SVM formulation. The half is just to make things a little bit easy. So we do have a half, right? And that's how we get the half basically in this Lagrangian term. Okay, so the important thing to keep in mind is that the dual formulation only depends on the inner product between the data points, right? So that's how I have this M cross M kernel here, right? And what this essentially means is that now I can define these kind of richer feature vectors from this phi, from these features xi, right? So what this means is that I can replace this xi now with a phi of xi, right? And this phi of xi could be basically an arbitrary kind of feature embedding. So for example, it could be polynomial features, right? So we saw for polynomial features in linear regression, we saw polynomial features in perceptron. So the phi here could be polynomial features, right? So I have exactly the same formulation with polynomial features, and I will get back the primal term, right? And in my primal also I will have the polynomial features, right? So what it means is that my primal will be minimum of half of w square, such that we have yi, right, multiplied by w transpose phi of xi, right, plus b is greater than equal to 1. Okay, and so instead of xi I have phi of xi now, and my w is in the range of phi of xi, right? So basically everything is same. This is all straightforward. I have my primal with my richer features, I have my dual with my richer features. Okay, but what is interesting is that with the feature vectors we can actually compute the inner products in a much faster way. Okay, so imagine that so in 2 dimensions, right? Suppose I just have my d or n, right? So my x vector is basically in r square, so I have x1 and x2, right? So then say my feature vector is x1 x2 x2 x1 x1 square x2 square, right? Then what basically I can do is that I take the inner product between phi x1 x2, right, and I take this between phi z1 z2, right. So I'm basically taking this between 2 points xi and xj. Here my xi and xj are x and z, right. I expand this out, right, and I get this very kind of nice term over here, right. So basically what this means is that even though I'm looking at this larger feature space, I can actually compute this much easier, right? And the way I can compute this is basically by defining, by essentially observing that my phi of xi and phi of xj in this case, right, where I just have basically the pairwise terms, right, is nothing but xi transpose xj square. Okay, so this is a very nice kind of intuitive observation. Okay, so what this means is that I can actually kind of expand this to come up with polynomials of degree d and define now my kernel of phi x transpose phi z to be exactly x transpose z raised to d, right? And in fact, I can kind of more generally define any feature map over here and define this SVM formulation in terms of a kernel, right? So in terms of a kernel now, I had earlier I had phi of xi transpose phi of xj. I can say, well, I can replace this with any arbitrary kernel, right? And with this, I get a valid formulation, right? And as long as from the kernel I can get back my phi vector, as long as I can do that, I can come up with a primal formulation for this. Right? But essentially, I have this kind of valid kernel machine with any kernel matrix K. Okay, so we saw that we can do polynomial kernels, right? Polynomial kernels essentially correspond to a phi of degree D, right? So it's basically a polynomial feature transformation, right? But more than that, we can actually also come up with things like, for example, Gaussian kernels, right? And we can also come up with general polynomials like this, which is phi transpose z plus c raised to d, right? But you can also come up with a Gaussian kernel. So a Gaussian kernel is exp raised to minus x minus z squared divided by 2 sigma squared. But what is kind of somewhat very strange with this, right, is that if you look back at the primal formulation, this corresponding phi is actually infinite dimensional. And the reason for this is that you can actually expand out the Gaussian here, right? And you can basically expand this out in this way, and then you do some more math, you expand the square out, you get this, right? So you get this by expanding the square out, and then you have exp raised to minus x square, exp raised to minus z square, and then exp raised to x transpose z. And now what you can do is that you use a Taylor series expansion for exp, right? And you can write this term, which is exp of x transpose z divided by sigma square, to be the sum of x transpose z raised to n. Okay, so you have basically these kind of inner multiplications, right? So you can basically take this out, and then this term you can actually expand into this x transpose z raised to n. So what this means is that this is actually an infinite degree polynomial. Okay, so if I want to come back to the primal space, okay, I'm actually dealing with this infinite degree polynomial feature representation. right? So that's why it actually makes sense to oftentimes stick to the dual space once you look at the kernel, right? And that's the reason why kernel machines are actually defined basically in the dual space. Okay, so one issue obviously, and this is what we saw time and again, right? So we saw this in regression, we saw this in perceptron as well, that as we increase the feature space, we have the possibility of overfitting, right? Now, of course, because we have a large margin solution, we are still generalizing better, but at the same time, we need to be a little bit careful, right? So we need to add some penalties to make sure that we don't have complicated solutions. So we need to do things like regularization, right, and slack. So we'll be looking at both of these concepts in the next few slides. Okay, so this is one caveat to know about kernels. Okay, so now I think we are at the kind of right time to talk about SVMs with slack. Okay, so we're going to kind of remove the linear separability assumption. Okay, so the simplest way to do this is to actually allow for misclassification. Okay, and we can basically, just like perceptron algorithm, just penalize the misclassification linearly, right? Now, of course, this is going to be much easier than counting misclassification, right? So if you remember the kind of 0-1 loss, right, we were basically counting the misclassification. So we were looking at something like the sign of y. We were basically looking at the sign of or actually maybe one kind of simple way to write this is whether basically you're looking at the indicator function of whether y equals to the sign of w transpose x, right? And this is of course a linear case. You could also do this in the with arbitrary feature functions phi. Okay, so actually one thing I'll say that we are back now to the primal space, right? So far we were talking about kernels, we were talking about a dual. Right now, let us come back to the primal problem. Okay, so we are dealing with W transpose X or W transpose phi of X, right? And then the 0-1 loss is basically exactly the indicator of Y equal to sign of W transpose X. This particular thing is very hard, right? And the way we can deal with this in the perceptron case, as we saw, is that we are basically saying that we basically multiply Y to W transpose X, right? And take the negative. And if this term is negative, that means that we are wrong, right? And then we basically linearly kind of look at this misclassification. So we'll be doing something like this basically over here, right? So we want to essentially kind of still have a convex formulation. Okay, so one of the main ideas we'll be using, and by the way, now we are actually when we look at slack, we will be looking at a formulation which is very similar to perceptron. So we'll come to exactly the formulation and how it looks. But before that, we'll actually start with the primal formulation, and then we'll come back to this kind of standard loss minimization formulation, right? And the main way we'll be doing this is that we'll be taking the constraints into the main objective, right? And with this, we'll be actually looking at something that we have seen as basically the sum of loss terms, which we saw in perceptron and linear regression. Okay, so how is this done? So far in the SVM, right, we didn't have this, right? So this part was not there. We just had basically this term, right? And similarly, this term was not there, right? But now we actually are going to kind of incorporate this, okay? And the way we will incorporate this is that we will essentially add this variable called the slack. So epsilon I is the slack, okay? So what this says is that when I do 1 minus epsilon I, I'm saying that this is the amount of misclassification. So I'm saying that I do not need yi multiplied by w transpose xi plus b, right, to be greater than or equal to 1, but I'm fine by reducing it by epsilon. Right? So if you remember, we had our decision boundary, which is y w transpose x plus b equal to 0, right? And then we had these two lines. So sorry, excuse my drawing. So I'll just try to draw this as much as possible to be parallel. Okay, so this line was w transpose x plus b equal to 1, and this line was w transpose x plus b equal to minus 1. Okay, and what we were seeing is that we have all our points lying on this side, right? and similarly we had all our points lying on this side. Now what I'm saying, right, is that there might be certain number of points over here, and I'm okay with that, right? And I'm okay with that as long as, right, it doesn't go more than epsilon. Okay, so that's the critical thing. I'm fine with a deviation of epsilon over here. So that's what this variable is saying. But I don't want arbitrary epsilon, right? So if I don't have any term over here in my minimization, so epsilon is the misclassification, right? So I don't want to have arbitrary amount of misclassification. I want to penalize for misclassification, right? So that's exactly what I'm doing over here. So by adding this term, which is the sum over I epsilon I, I'm controlling for, I don't want too much misclassification. I'm okay with some misclassification, right? And then now I have incorporated, basically I have three sets of variables. One is W, one is B, and this is the epsilon R. The epsilon also gets incorporated here. Okay, so now the critical question is that the way I can control the trade-off between my W and my misclassification is through this notion of this variable C. And C is what we call basically the hyperparameters. Okay. So how does my objective change with C? Okay, so as C goes to infinity, right, what I'm saying is that I better have my epsilon I going to 0. As my C becomes really, really large, I say that I care more and more about my epsilon I, right? So you can clearly see that if basically C goes to infinity, if C is very, very large, right? Even if epsilon I is like small, which is like 0.00001 or whatever, right? It's super, super small number. I'm multiplying this by epsilon, my loss will go to infinity. So the loss will try very, very hard to make sure that I get a perfect classifier. Okay, otherwise the loss function is infinite. So C goes to infinity, we get back the linear separability. Okay, now what if C goes to 0? If C goes to 0, I'm basically saying that I don't want this term at all. If I don't want this term, I have arbitrary epsilon, arbitrary W, right? So I will essentially allow for arbitrary classifiers and completely ignore the data. So obviously that is also bad, right? So we want, we basically want something in between that can take care of the trade-off between these two, right? And that's why C is actually called a hyperparameter. Okay, so how can we pick C? And the standard way of doing this is basically using a validation. Okay, so this is in fact true for any kind of hyperparameters. Okay, so in machine learning, this is the first time we actually saw a hyperparameter in machine learning, right? Because the first time we saw somewhat of a non-trivial classifier through SVMs. And C is this hyperparameter, is also called the regularization hyperparameter. And we'll see why. We'll see the relationship to the regularization in just a few slides. Okay, but C is a hyperparameter. Any hyperparameter in machine learning is basically chosen in this standard way for the most part. Okay, so I divide the data into three pieces: training, testing, and validation. Right, so I have training, testing, and validation piece. And on the validation piece, I basically tune my hyperparameters. So I want this to be different from training and testing, right? So training is where I train my model. Then I have a validation set. Okay, I train multiple models with multiple C, right? So say I have models M1 up till MK, right? So I have K models. I tune my hyperparameters by picking the best among M1 to MK. Okay, on my validation set. So I tune my hyperparameters on my validation set, get the best model from M1 to MK, right? And finally on my testing, I evaluate it. So you see with this process, there is no cheating, right? I have a different set on which I've done my training. I have a different set on which I do my validation and pick the best model. And I have a different set where I report the accuracies. Okay. It might be possible though that what is the best hyperparameters on the testing set may not be the best on the validation set, right? But that's fine. I mean, that's the best I can do, right? So as long as I have a reasonable range of my hyperparameters, right, it will do reasonably well on my testing set. And my testing set, since with my evaluation, I will get the accuracy. This is kind of the real world deployment. I go ahead and deploy this in the world. That's like another test scenario, right? Once I deploy this in the world, I don't have any chance to kind of retune my hyperparameters. That's why it's very, very important to actually evaluate on the test set, because that is how we'll get a realistic understanding of how the algorithm will work. Right? Obviously, there is no distribution shift, there is IID and all of those assumptions hold. Then when I deploy this on the real world scenario, I should be able to see the same performance of the model. Okay, so that is the kind of critical thing about hyperparameter tuning. I hope this part was clear. Okay, so this is going to be the general strategy. I build a classifier on my training data. I select my hyperparameters using my validation data. Right, so I basically have my I essentially, okay, so I have M1 to MK as I said, right? And each of my model is with hyperparameter, let me call it HP. This hyperparameter configuration 1 to hyperparameter configuration C, right? So for example, each of these are different values of C. So this is one C1 to CK. For example, I can take my C1, typically how this is done is that I take my C1 to be say 1E minus 3. Right, and I multiply each of this bit by 10, right? So I take my C2 to be 1E minus 2, take my C3 to be 1E minus 1, right? And I'll go ahead with this till maybe my CK is 1E plus 3 or plus 4, right? So basically I have swept through this entire range. So over here I have roughly what, 7 or 8? I have roughly 8, right? So basically K equal to 8, I think. 7 or 8, I can't do the math very quickly right now, but yeah, so I have essentially those many number of hyperparameters. Okay, this is the standard way of picking the regularization hyperparameter C. Okay, so once I have these models, I pick the best model, right? Pick among M1 to MK, right? And finally I evaluate this, and this will give me a realistic understanding of deployment performance. Okay, so that's when if I tell my boss, for example, right, he asks me, okay, I've trained this machine, I'm a machine learning engineer, right? And my boss basically asked me to train a new model for a particular task. I train it, I do all of this, and I say, okay, I've run the test. I can expect that I will get 95% accuracy. This is how I can tell about the 95% accuracy and nothing else. Okay, if I either base my accuracy on my training set or on my validation set, I will be wrong. Okay, that is not the correct way of doing it in machine learning. We absolutely need to use a held out validation set for hyperparameter tuning, a training set, and a held out test set. Okay, for getting realistic understanding of deployment performance. Okay, so I guess this is just the same thing. I think it's like super critical. That's why I've kind of dedicated 3 slides to this, right? So I gather data and labels, right? I select my feature vectors. So this part is basically data gathering. This part is basically feature engineering, right? And then I split my data into 3 sets: training, validation, test set, right? And the experimentation cycle is I select a good hypothesis from my hypothesis space. Okay, so this is my model class. Then I tune my hyperparameters using a validation set, and of course I basically train models on train set. So here I will have a loss function, I will have a learning algorithm, and then I'll do the training, I get the models, right? Finally, I compute the accuracy on the test set, and this is what I will be basically kind of announcing that this is how my model works. Okay. All right, so now we will again come back to SVMs with slack. Okay, so I have minimum of W comma B comma epsilon, half of W square plus C sum over epsilon I. This we saw is a number of misclassifications. Okay, and then I have my constraint over here. It has epsilon I, and epsilon I is greater than or equal to 0. Right. So what is the optimal value of epsilon for a fixed W and B? Okay. So this is easy to see. So in fact, note that if yi multiplied by W transpose xi plus B is greater than or equal to 1, right, then my epsilon I is equal to 0. Okay. But if yi multiplied by this term is actually less than 1, strictly less than 1, okay, then I can exactly set epsilon I to be 1 minus yi multiplied by W transpose xi plus B, right? So as long as I have basically for my given W, once I have a W, right? Once I have found my W after my learning, I will be able to set my epsilon in this way, right? Because obviously for when the optimization is complete, I will be kind of at the boundary, right? Because in some sense, since my yi multiplied by W transpose xi plus b is strictly less than 1, okay? So if it's greater than 1, then I don't care about this, right? Then my epsilon I is 0. But if it is strictly less than 1, okay, then I need to measure how much I am deviating, right? And that will be the value of epsilon that I'll be using. Okay, so this is very, very intuitive. I don't really need to do too much of optimization, but just kind of look closely at the math here. I can figure out epsilon, right? But this automatically gives me a formula for epsilon. So what this means is that I can actually set epsilon to be max of 0, 1 minus yi multiplied by W transpose xi plus b. Okay, so this is awesome, right? Because since now I have explicitly this formulation of epsilon, I can put epsilon back over here, right? And essentially with this, once I set epsilon I in this way, I don't really need my constraints anymore, right? Because my constraints are automatically handled when I'm setting this value of epsilon. Okay, does this look familiar? Well, this is exactly the Hinge loss, right? So once I do this, you get this very nice formulation of support vector machines of basically the Hinge loss, right? And this is basically only possible because I have taken slack into account, right? So anyways, I have this C multiplied by a max of 0, 1 minus yi multiplied by W transpose xi plus b. Okay, and this function is exactly now in terms of what I had, right? Except that there is one slight change. I have this half multiplied by W square, which we had not seen before, right? So essentially this term is the penalty of preventing overfitting. It's also called regularization. Okay, and this term is basically the Hinge loss. All right, so now we kind of introduce regularization, right? I think regularization is, I have hinted about regularization in the past, right? I've spoken about this as a technique to avoid overfitting and basically kind of focus on generalization, right? But regularization, I think, is one of the most important topics in machine learning from a practitioner perspective, as well as from a, from an empirical perspective, as well as from an algorithmic perspective and from a theoretical perspective. Okay, so so far we have seen problems of this form, right? I didn't actually introduce any regularization. I just said that we can minimize the sum of the losses, right? So in the case of linear regression, we saw that L was the square loss. In the case of perceptron, L was the perceptron loss, right? Essentially, we can now take this version and get a regularized version for each of these cases. For perceptron, we can do this, and we can do this for linear regression as well. In perceptron, it becomes slightly different with regularization, right? But in linear regression, typically this is what is oftentimes used. You don't just do linear regression, you actually have a regularization oftentimes. Okay, and C is this hyperparameter. Okay, this is also called the regularization hyperparameter. Sometimes in some places it is also called lambda, right? So actually the way it is oftentimes, sometimes it is written is I have a sum of my loss function of f of xi comma w comma b of yi, right, plus lambda by 2 multiplied by w square. Okay, and in this formulation basically lambda is 1 by c. So you can write it either ways. Okay, lambda then over here is basically called the regularization parameter. All right, so now I'll just spend a few minutes talking about this important difference between perceptron versus Hinge loss. So we start with that. So actually maybe I'll start with the squared loss first. Okay, so we saw that this is basically I have my f of x comma w comma b, right? And this term basically in the linear case is just w transpose x plus b, but it could be arbitrary, right? And I have my y, right? So this is my loss. Okay. In the case of the 0, 1 loss, right? In the case of 0, 1 loss, we basically wrote this as indicator of, and by the way, typically you have the sum over these, right? But I'm just writing this for one instance, x and y, right? Just basically one pair x and y. How do you measure this loss? Okay, so this was indicator that I better make sure that the if I'm using, so I take this as a sine of f of x comma w comma b should be equal to y. Okay, so this was a 0 1 loss. If it's exactly the same sign, then it is 1, otherwise it's 0, right? Another way to write this actually is, I think you can write this as half of the difference between sine of f of x comma w comma b minus y, right? So we saw that if y and the sign don't match, right, then it will be minus 1 and plus 1, then the difference will be 2. And since the absolute, this is the absolute value over here, so actually I don't have this, I just have minus y, right? Okay, so this is the 0 1 loss. We saw that the hinge loss is L of comma y, right? And the hinge loss basically was where you essentially kind of replace this with a max of 0 comma minus f of, or actually, so it's minus of y multiplied by f of x comma w comma b. Okay, and by the way, I'll just write this for now. Just think of this to be w transpose x plus b, right? So if you put this over here, we get minus y multiplied by w transpose x plus b, which is basically the perceptron loss, right? And the hinge loss is nothing but max of 0 comma 1 minus y of this term, right? Which is very, very intuitive. So what's going on? Okay, so if I plot on this axis, if I plot this basically as my, okay, sorry, this is not y. If I plot this as my loss function, okay, and I plot this term as y multiplied by f of this, right? If both are of the same sign, then the 0 1 loss, I have this to be, I'll just take a red, right? So I have this to be 0, otherwise I have 1, right? So this is a 0 1 loss. Okay, so I'll use maybe a slightly different color. Say I use blue, right? We saw that the perceptron loss was, again I have this to be the same thing, right? But then now I have this line over here, right? So this is the perceptron loss. Okay, and the hinge loss is, again I'll use a different color. Okay, the hinge loss starts with 1, so it is 1 minus, so there is a slight margin over here, right? And basically I'm saying this is max of 0 comma 1 minus this. Okay, so what this means is that if I'm somewhere over here where y of y multiplied by f of sorry, just give me 1 minute. So yeah, okay, right? So I have basically, imagine that my y multiplied by f of x comma w comma b, right, is say half. Okay, if it's say half, then actually the max of 0 comma that quantity will be positive, right? So if it's anywhere less than this, I start having an error, right? So what it means is that the the hinge loss essentially is this, right? So what it means is that if my y multiplied by f is small, right, even if it's greater than 0, if it's like say less than 1, I have this margin of error to be 1, right? I start getting an error. So in some sense, my hinge loss is basically being a little bit over cautious, right? And thanks to this, it actually kind of helps in generalization. Okay, so this is the difference between the perceptron loss over here, right, versus the hinge loss versus the 0 1 loss. One interesting thing is that the hinge loss is always greater than the 0 1 loss. Okay, so the hinge loss basically upper bounds the 0 1 loss. Okay, So this is great, right? So now we understand the hinge loss versus the perceptron loss versus the 0, 1 loss. I also have the square loss, but I'm not considering the square loss right now because the square loss is slightly different. But just for completeness, I'll basically kind of write down the square loss here. So the square loss has the error, right? But the error now kind of depends a little bit differently on this term, right? So this axis basically is actually now y minus f of x comma w comma b, right? And it looks basically like this. The error grows as a square of the value of y minus f of w comma x comma w comma b. Okay, so the square loss is not actually as commonly used in regression, right? And maybe this is a homework question for you to think about, why the square loss is not actually as commonly used in the case of regression. All right. So one thing that oftentimes data is imbalanced, right? And essentially SVM kind of very naturally can deal with that, because I can separately kind of penalize my errors on the number of positives and number of negatives, right? So if n plus is the number of positives, n minus is the number of negatives, then I can kind of separately treat the two. And then I do basically epsilon I divided by n plus and epsilon I divided by n minus, and I can naturally in some sense deal with this imbalanced data. Okay. All right. So now we saw the primal formulation, and we connected this back to the hinge loss. Okay. So the question is, what is the dual? Well, you can actually do the dual. Well, we saw the dual where we didn't have any slack, right? The question is, what is the dual if we have slack? Okay. So this is a little bit of involved math, so I'm not going to right now go into a lot of detail, but I'll just give the high level idea, right? So to start with the primal, I have additional variables epsilon I, right? So note that what you'll have to do is that you'll have to take all of this on this side. So basically you replace this by 1 minus epsilon I minus yi multiplied by this term. Okay, so I have 1 minus epsilon I minus yi multiplied by w transpose xi plus b, right? And this is basically less than equal to 0. And then I have minus epsilon I also less than equal to 0, right? And then basically I take both of these into my Lagrangian term, right? So my Lagrangian, you can do the math and you will see that my Lagrangian exactly comes up with this, right? I now have basically two variables. I have my lambda I, right? For my lambda i's corresponding to this, and then I have my mu i's corresponding to this epsilon constraint, right? So this is my mu I over here corresponding to my epsilon constraint, and then I have my lambda i's corresponding to the data and slackness constraint. Okay, I take the derivatives with respect to w, with respect to b, with respect to epsilon, right? When I take the derivative with respect to w, by the way, I get this relationship between, which we saw in the standard case as well. This does not change, right? So my w is now again this linear combination over lambda I, yi, xi, right? Which is good. I have this linear combination over my data points once I have my lambdas, right? From this, I basically get the constraint that the sum over I lambda I yi must be equal to 0, right? And from this, I get the constraint that C is actually equal to lambda k plus mu k. Now actually note, right? Note that my lambda k, okay? So basically both my lambda k is greater than or equal to 0 and my mu k is greater than or equal to 0. Right? The reason for this is because both of these are inequality constraints. Both of these are inequality constraints, right? So if you remember from the Lagrangians, once you have inequality constraints, you require basically the lambdas to be greater than or equal to 0, right? Because of this, what you essentially get, so because mu is greater than or equal to 0, you get that actually lambda k is less than C. Okay, so that is exactly what you kind of get over here, and then you actually don't require your mu's anymore, right? Because the only place where mu, okay, so it's actually one more slight detail is that if you kind of expand this, because of this fact that C is actually equal to mu k plus lambda k, I will focus on the following terms, right? So I'll just kind of use a different highlighter. Maybe I'll use this color, okay? So I focus on, yeah. So you basically focus on this term, which is C multiplied by this, right? And then you focus on lambda I multiplied by epsilon I. So basically you take all of these slack parameter terms, right? So I have C minus lambda I minus mu I, looking at this, right? And I get 0. So basically what this means is that in my dual formulation, I will not have any epsilon I. My epsilon I actually gets cancelled away thanks to the sum of these three. So if you do the math, right, I just kind of went over it in a slightly high level, in a kind of a hand wavy manner. But if you do the math, you get a very similar dual formulation to when we didn't have the slack variables, right? And I have the same constraint. Now the only thing is that my lambda i's are actually bounded by C. This is the only additional constraint I have, that my lambda I should not be too large, right? So in some sense, this is where regularization comes in the dual. Okay, by ensuring that my lambda i's don't become too large, I'm kind of explicitly making this assumption in the dual, right? I am essentially adding regularization. So I think this is a kind of very interesting connection between regularization and the dual formulation in the SVM case. Okay. All right, so we argued intuitively that SVMs will generalize better than a perceptron, and I think one of the reasons was basically margin, and the other was generalization through regularization, right? So we have regularization, and through that I'm kind of achieving generalization, right? How do we make this more precise? So actually this we'll see in the next few classes, particularly when we talk about kind of the ML theory, right? And we look at some learning theory, basically, I think in maybe 2 or 3 classes. So that time we'll actually take a closer look at making this more precise, okay? So our kind of roadmap on the next few lectures. So now we are done with SVMs, okay? So the next lecture I'll focus on k-nearest neighbor and decision trees. And then the two lectures after that, I will focus on learning theory. Okay, and with this, I think we'll kind of get a good understanding of slightly more complicated machine learning models and some theoretical tools to analyze generalization and things like that. And once we are done with that, then we'll actually look at probabilistic models. We look at things like logistic regression. We look at naive Bayes, and so on and so forth. Okay, so thank you so much. This is the end of lecture 6, which is SVMs with Slack.